Well, good evening, one and all. Welcome to our evening focusing on citizen science for us this week. We've got a high school student with us for the second part of the evening. And to kick us off, we've got Dr. Chuck Higgins, who, like many of us, is passionate about engaging youngsters in science and technology, and has a passion for outreach. So, Chuck, with no further waffling from me, I hand over to you, Chuck.
Oh, thank you very much. It's nice to have the invitation. Nice to talk to you. Let me share screen here, and I need to start my, there we go, and I'll share. I'm disabled.
Oh, did I not? You should be okay. Have another go.
All right. It says disabled screen sharing.
Okay, let me just switch that over and then back again.
Okay.
Right. Have a go this time.
Now it's telling me disabled.
Oh. I definitely. Yeah, have a go now.
There we are.
Sorry about that.
Quite all right. There's too many platforms, and then all the buttons are in different locations, it seems.
You're right.
Okay, and I want to make sure I share sound. There we go. Okay.
Looking good.
Great, great. Well, again, thank you for the invitation. I'm Chuck Higgins. I teach at Middle Tennessee State University, so I'm in the heart of the state of Tennessee, the geographic center, not too far from Nashville, if you know where that is. And I am also part of the Radio Jove project. Some of you may be familiar with that. And I'm going to talk a little bit about Radio Jove and citizen science, our connections with it. And I have 30 slides, so I'm aiming for about 30 minutes, 30 minutes plus, and then hopefully give plenty of time for questions. But I'm completely happy to take questions midway. If somebody wants to put a hand up or something, I'm happy to do that. Or if you prefer, if you want to wait and do it later, that's fine too. So Radio Jove is started in 1999 as a education outreach project, and many of our team members are listed here. And the goal was basically to get people interested in science, using radio astronomy as the tool. And so recently, however, we've sort of changed our due to some funding, and also the onset or the buildup of the ability to do some citizen sciences. We sort of switched our focus a little bit more towards the science. And so now we're calling it 2.0, and we've got several regular contributors to Radio Jove, and they're listed here in green. And I just highlight that Radio Jove project is a NASA partner project. So we do get some funding from them, and we partner with an education group called the heliophysics education activation team, so the HEAT group. And so call attention to them as well. So we're interested in helping people learn and do science. So I'll talk a little bit about, give an introduction and talk about 2.0, and then do some, talk about our citizen science. So with apologies for preaching to the choir here, why do we do it? Why are we interested in radio astronomy in the first place? And I watched a little bit of the video from last month, and Paul, you like the quote because it's fun, and it certainly is. There's a thrill to it, and using your own radio telescope, hopefully to receive cosmic radio signals. That's pretty cool. But of course, scientifically, we do it to study the universe, and by using radio telescopes, radio astronomy, we can learn something different about the universe. So my favorite picture is to show the M81 galaxy group optically and then in radio, and you see a whole level of detail in the H1, the 21 centimeter maps that you would not ever see optically. So that's scientifically using a different part of the spectrum to teach us something about something different about the universe. And so I've got a picture of Jupiter there, showing you the plasma torus region. So, and even the plasma that make up the what am I'm blanking on the radiation belt. Sorry, the radiation belts there at Jupiter. So you never see that optically, and so just to give you a different picture, and of course these incredible images that we're getting here recently on the center of our galaxy and in other galaxies, the supermassive black holes. So amazing science there, and listed a few other major discoveries in radio astronomy. So again, let me play a little sound file here in case some of you have never heard what a solar burst might sound like. So
Chuck, can I just break in 1 second? Could you make your PowerPoint window full screen sized? Because it's be a little bit easier to read for everybody.
absolutely, I can just expand it, or
yeah, just expand it. I think that'll do the trick. Thank you. Sorry to interrupt.
Not at all, not at all. Happy to do that. Is that better? Can you see it better now?
We still see part of the tent in the bottom right.
Okay, I'm leaving the screen open so I could open up chat and see some of the chat, and also I might switch screens here in a minute.
That's fine. This is much better than before. Thank you.
Okay, you're welcome. Yeah, thank you. So organized white noise there, right? And to some that's beautiful, and others that's annoying. That might be interference to some of you. But this is some citizen scientists working with Radio Jove, showing a solar burst that happened a couple of years back, and you're seeing essentially on the right-hand side, the old Radio Jove single frequency, 20.1 megahertz center frequency plot of the antenna temperature as a function of time. So that's what several solar bursts or typical solar bursts look like on a strip chart. And then the Radio Jove 2.0 is our new spectrograph. And so this one happens to be 15 to 30 megahertz as a function of time there. And you can see a lot of spectral structure in the solar burst there. So quite an impressive level of detail with amateur, semi-amateur equipment. All right, let me get out of that. There we go. And now what about Jupiter? Have many of you heard the sounds of Jupiter? So let me play a couple files here.
Following is Jovian S-burst activity.
So each one of those little pops is seems to be unique to Jupiter. And Jupiter actually has some unique sounds to it. So not only on an intensity time graph, the characteristics of the Jovian emissions and what they look like, but also in what they sound like. Now, each one of those, if you record this at high rate and play it back, you can slow it down, and here's what those pops sound like. Well, I'm going to play this. So very Whistler-like. And what you're, now that's professional equipment there, making those recordings on magnetic tape, but high-speed magnetic tape. But what you're hearing is the different frequencies coming from the different radio frequencies that are generated in Jupiter's magnetic field. And the cartoon there on the right kind of gives you a picture of where some of those emission zones are located in the magnetosphere. And some of those are connected to the interplanetary magnetic fields. And so you're getting plasma that is solar. And then some of those emission, we draw it as a cone. These emission regions, these cones are associated with plasma that is connected to the Jovian moon Io and the plasma torus that surrounds Jupiter. So the different frequencies that you hear are telling you the different areas where the emission is being generated. Its frequency and the magnetic field are directly related. And so the higher frequency radio emissions are happening closer to the planet. And the direction of, in some cases, the direction of the electron motion. So these are emissions are caused by spiraling electrons in these magnetic fields. So the way the frequency is changing tells us something about, also tells us something about the motion of those electrons within the magnetic field. So radio astronomy, like all astronomy, is essentially remote sensing. And so we are remote sensing the radio wave generation zones in this case, the magnetic field of Jupiter. And hence our name is Radio Jove, because we started with a love of the radio emissions from Jupiter. So and Jupiter happens to be the only other planet that you can detect. The radio signals are strong enough to be detected with simple equipment on the ground. So all the other planets that have magnetic fields do emit radio waves, but they're not capable of reaching the ground. Again, a review for most of you, but this is just to identify many of the sources of natural sources of radio emission. Of course, the sun emits radio emission, but not in a way that you would expect, right? Hot objects emit Planckian block body radiation, and so the hotter the object, the more the stronger the emission at all wavelengths, right? So that's the idea of black body radiation. But even stars are not hot enough to emit a lot of thermal radio waves. You'd have to, the star has to be much hotter. And so the radio emissions that we get from stars and the planets are by a non-thermal mechanism. So moving charged particles in magnetic fields. So not only do you have different sources of radio waves coming from solar system objects, but certainly objects in the Milky Way, supernova remnants, star formation region, of course, hydrogen, H1 clouds that are pervasive in the galaxy, the galactic plane. But then, of course, you have lots of extragalactic radio sources, quasars, other radio galaxies. Of course, even molecular line radio emissions. But so the two categories of emission mechanisms, as I mentioned, thermal emission, because the object is hot, can generate electromagnetic waves, and interactions between particles, protons and electrons, gives us the Bremsstrahlung emission, the free emission, and in certain cases, spectral line emission. But then the non-thermal type emission are the cyclotron or synchrotron processes that we're hearing from solar radio burst and those from Jupiter. And then, of course, pulsar type emission or gyrosynchrotron emission, also non-thermal. So Radio Jove, as I said, have been around 20 plus years. And here's our website. It's, we're hosted by Goddard Space Flight Center website there, gsfc.nasa.gov. And so that's a way to find out the latest, best information about Radio Jove. And you're certainly welcome to visit there anytime. This slide just represents our old Radio Jove kit. So again, about 20 years, we sold Radio Jove simple radio receivers that you can buy and build yourself. So they were simple enough that a high school student essentially was our high school level of knowledge and ability and above to build this. But we've had even middle schoolers get involved, but it became too cumbersome to keep ordering and keeping these parts in stock. So we last year stopped selling these, and it's kind of a disappointment because we love these kits, but that opens the door to our 2.0 and our newer system. But this just shows you the old receiver and the antenna. We used a 2 dipole, a dual dipole antenna. It's simple to construct. It's certainly takes up a lot of real estate. That's the unfortunate side, but at the HF band, that's kind of what you have to deal with, of course. But we like the dual dipole for a couple of reasons. It gives us a little bit more gain. Single dipoles work fine, but the Jovian signals are just too weak. Many of them are too weak to be detected with a single dipole. So extra dipole gives you that added gain and a little bit of directivity, not a whole lot, but to pick up some of the weaker signals. So this was part of the original kit, and there you see some solar radio bursts with this initial kit, and the software was included with it as well to take the signals, the analog signals, use a sound card, either internal or you can use an external sound card, and digitize the display and use your computer as your recorder, essentially. And so that again worked very well. We sold more than 2,000 of these, more than 2,500 of these kits over 20 years. And but now sort of turned a corner to a digital spectrograph system. So now we are able to do a little bit more science with this new system. So sort of our change of direction into doing more scientific studies and involving citizens to help us take data and even analyze it. So the new system is a spectrograph, so a multi-frequency radio telescope to observe, again, Jupiter, Sun, Milky Way background, and even Earth radio emissions. And so we're trying to inspire, just like we did before, and teach and provide an experience for those to learn something about science in general, but radio astronomy, and we hope to guide people to become from amateurs to becoming more experts. So we invite anyone to be a part of Radio Jove. So we have lots of the general public, and of course, almost by definition, those are radio enthusiasts, and some astronomy clubs and high schools and colleges and universities have gotten involved. So that's sort of some of our goals and the reason we're here. And here's the new kit. So there's nothing really proprietary about any of this. The instruction manuals and the construction manuals for the dipoles are all on our website, but we're now using SDR receivers. They've just come so far and so quick that they're pretty amazing, and we're using the one by SDR Play, so right in your neighborhood. And so we still use our dual dipole again to make it easy to construct and or make it portable, and now the software that comes with it. This is free software. One of our founding members, I'm not sure if Jim Sky was a founding member or very soon after, he wrote the radio SkyPipe software for single frequencies, a digital strip chart for your computer. And he also, we got funding to do this, develop this Radio Sky spectrograph software. So many radio astronomers, us included, prefer the display to be a frequency time instead of a waterfall. We use a frequency time chart to record, display our data. And so the Radio Sky spectrograph software does that. So it's the unfortunate part about this is, of course, the SDRs are, black boxes in a way. So you don't get to build it like you did the old Radio Jove receiver. But that's something we just had to let go and change our focus a little bit to the more science related topics. And so that's our new system. We're having in particular, the model that we use is the SDR Play 1A, RSP 1A model. So that's their entry level. And there's some pluses and minuses with that. It's certainly the lowest cost in their line of receivers, and but there's some negatives to it with a large noise temperature. The receiver noise temperature is fairly large, but not so bad that we can't use it for our solar system radio science. So here's the kit cost as it is. So here's what's included, and we give you the option of building the antenna yourself, or we'll pre-solder the wire and the coax for you, and you have to, of course, provide your own antenna mounting support structure, and but we give you that option if you want to build the antenna yourself and make it a little bit cheaper. And so these are about the same price as the original Radio Jove kits. So that's another reason to change it up here. And as I said, there's nothing here that you can't purchase yourself. And the assembly and setup manual for the SDR Play receiver is all online. You can buy these kinds of things and the cables all yourself. We're just doing it to make it easy for people who don't want to go chasing parts or things. So we provide all the cables, connectors for you, and to get you going. So let me switch my screen here. I wanted to show you this from one of our near professional amateurs, Larry Dodd. He's down in Georgia. You can actually, he's got his system streaming. Let me see if I can share my screen here again. Let me unshare. Sorry about that. And let me reshare with my web browser here and find the play button here. And so Larry rigged up his SDR Play to YouTube. So he's got a live stream of his observations. This is North Georgia, USA, and it's great. It's the simplest way to get started. You don't even have to buy your own equipment, and he audibilizes, I think, the 20 megahertz band. And the RSP-1A model has a bandwidth of about 8 megahertz. So we're displaying here. He's got it from 17 to 25. Yeah, of course, that's the beauty of the SDR. You can change your bandwidth pretty easily there. So I just wanted to show you that was a one way to see what the HF spectrum looks like in North Georgia. And when you get a solar burst or some Jovian burst, it takes a a little bit of practice to get to be able to recognize those things, but strong solar bursts are very easily identifiable. Let me go back to my PowerPoint here. And where am I? Right here. Okay. Okay, there we are. And I should say that Larry and a colleague developed a way, because we get this question all the time, is do I have to use the SDR play? And at the moment for Radio Jove, that's what we're using, and we are trying to make systems as nearly identical as possible to help us with the science questions. So we're trying to get systems set up around the US and around the world too, to with a similar kind of antenna and a similar setup, so that we can easily compare the radio signals. Larry and his colleague developed something called SDR console that allows you to use other SDRs. And I should be clear here that to be able to display your data using our Radio Sky spectrograph software. So that's what the console does. And certainly there's, oh gosh, dozens of SDRs out there that are reasonable. The real inexpensive ones, the dongles and things like that, will work, but they typically don't have a good enough dynamic range to allow you to pick up all the Jovian and the solar data. So we were able to characterize the SDR 1A model, SDR play 1A model a little bit. And so far that's working with us. And that's the one that we use and recommend. And frankly, you know, we're able to help people get that one working. Some of the other SDRs have their own, you know, software that comes with them or whatever. So we're not experts on all of them. So that's part of why we're trying to maintain a bit of a focus too, so we can help people, beginners, get a system working. Sorry, I need to go to that mode. And so here is, you know, I have this set up in my office here, and I don't know, behind me you can see a couple of dipoles sitting up, leaning against my blocked out window. I have a westward facing window here, and sometimes it gets too bright and I have to block it out. And I prefer a real background, I suppose, an artificial one. But there you see the scale of, you know, the SDR play and a few connectors, and SDR play has its own software, of course, and so you can control the receiver that way. But we have an intermediary piece of software called SDR Play 2 RSS. So that's now sort of been combined with the Radio Sky spectrograph software, but that allows you some direct control of the receiver. So you can set the bandwidth, you can set the filtering and the gains on, and any of you've ever played with these things, you know that there's it seems like 1,000 options on these things. So part of the reason, again, for using this model and is we can tell you the settings that work best for doing Jovian or solar radio astronomy, and we leave it up to the individual to change things and learn and adapt the system however they want to. But that also makes it easier for a beginner to get involved. So here's a link again off of our main website, just to showing you that the assembly manuals are there. And a few example observations. So you heard and saw some solar bursts before. So that's again a 16 to 24 megahertz frequency time spectrogram, and this is 40 minutes of data there. It's hard to read those axes, but that's 1520 UT to 1600 UT. And so very interesting type 3, and then it looks like even some type 4 solar bursts there. Below that is some Jovian radio emissions, and this is characteristic of an Io related Jovian emission, and those are given the name A, B, C, and D. But so a single frequency, it's much more difficult to identify Jupiter versus background noise. But with the spectrograph system, the characteristics, the spectral characteristics of these emissions are much different than local interference or other sources of radio emissions. So that makes it easy to identify some of these. In some cases, horizontal bands there, of course, are either local stations, local interference, and you even see some Faraday. I don't know if you know these kind of curved lines that you're seeing here. This particular observer has a square array, an advanced antenna, wideband antenna that we can do polarization measurements. So this is right-hand circularly polarized Jovian emissions, and so those emissions will the polarization, the axis, will rotate as the waves propagate through the ionosphere, and you can see that as these Faraday bands in the Jovian emission there. The upper right picture there is something one of our citizen scientists noticed, 10 years ago, and it's just been kind of we've been seeing these over the years and gnawing at us. And then one of our colleagues at NASA decided to look into it a little bit and wrote a paper on it. And so these, we think, are coming from lightning discharges, distant lightning thunderstorms that are moving relative to the observer, and of course using the ionosphere as to reflect these signals, and you get this triangular pattern. And this again, one of our amateurs noticed this thing, and it led to a scientific publication. So that is a perfect example of someone getting involved as an amateur and then learning more, doing more, and then becoming part of the science process or the scientific process. So terrestrial emission there, and then there's some more light solar bursts there, and the lower right-hand figure, and then the diagonal lines show radar, ionospheric radar sweepers that you can hear a lot of times, and then they're very clearly seen in the spectrogram here. A few more. This is some more solar bursts, and in this case, this was data that I detected a couple of years back, both with a single frequency radio Jove setup there, put on top of the radio spectrograph, and you see it, it looks like about 17.5 megahertz down here. Very strong local station there, bleeding over a little bit. So the SDRs tend to overload in some cases, depending on your gain settings. So that's kind of local interference there, but very clear solar radio emissions there. And of course, sometimes the sun is strong enough, the flares will X class flares will change the ionosphere enough and cause it to become absorptive, and so you get radio fade outs, which I know many of you are very familiar with. But here you can actually see it in some of the background and even some of the interference stations in some cases become much weaker after these, and you can tie them back to, in many cases, to a particular flare from the sun. So the basic kit that I talked about before, you see a few $100s. You can like any hobby or passion, you can spend as much money as you like on some of this stuff. So there are advanced equipment. So this is a terminated folded dipole. So it's a wideband antenna, and it's a square array, and the two outputs then will allow you to get right hand and left hand circularly polarized data, and that gives you more scientific capability. And for us Jupiter observers, that's important, because I should have mentioned this before, but the radio emissions that's coming from Jupiter are highly circularly polarized. From the northern hemisphere, predominantly right-hand circular, and from the southern hemisphere, left-hand circular. So having a circularly polarized antenna will allow you to pick up the Jovian emissions a little bit easier. The sun, not so much. It's mostly unpolarized, but so you can do more advanced antennas, use more advanced antennas, and calibration. Of course, that's very fundamental to science. And so the old single frequency receiver, we had an optional calibrator for those who wanted to calibrate their system. And for this new system, we don't yet have the calibrator that you see here is $500, custom built. So we are working on a do-it-yourself calibrator that you could build, and we have one working on the bench, and we're going to make those the instructions and a parts list available for those who would like to maybe build one themselves. So the point here is it's a little more complicated, of course, to calibrate a multi-frequency system. So we're gonna, but we need to do that, right? And to gather good science data. So that's something on our plate, as well as to try to teach observers and give them the tools to make accurate timing, because that's important if you're going to compare signals from different stations, and then of course polarization too, if people wanted to do that. We do have a data archive, so any Radio Jove participant can create an account, free of charge, and archive their data on our Radio Jove archive. And we encourage that. Of course, that's good science, and we have a searchable archive, and some of the more advanced data from our more advanced citizen scientists are those data are going to another archive, the Planetary Data System archive. It's being vetted now at UCLA, but we want to make those data also available for more science-related questions. And so speaking of that, just to kind of finish up here, we've got a few citizen science projects that we like people to help us with. And of course, is just generally making calibrated observations of Jupiter and solar emissions. And this year in particular, due to some of the funding, we are making a concerted effort to try to get as many observers. Now for these two eclipses, this would be North and Central America, to try to get as many radio observers observing the event to see if we can detect differences in the ionosphere with the lunar shadow over your location, for whether in totality or very, very close to it. So we're going to be pushing a campaign to try to get people to set up and record data over several days, certainly before and after the eclipse. And we would like to get people to make what we call a quiet day curve. So essentially setting up a Radio Jove system at a site and taking data for an entire year. And analyzing those yearly data, you can create a, you eliminate the sporadic interference, and you create a background curve due to the Milky Way. And then you can use that in the future as a way to calibrate the level of any signals, above that galactic background. So that's a quiet day curve. And then like that terrestrial propagation we're calling TPs, we're using those to help us understand sort of the nature of the ionosphere and how radio waves propagate through the ionosphere. And something that I started with some of my undergrads many, many years ago was, what does a solar radio burst in the HF count look like? Does it follow the sunspot number? And so that was just sort of a fancy initially, but I've got data through, you see, about mid 2018, so I've laxed a bit there, but I'd like to keep that going and to try to provide a solar radio burst count, like a sunspot number count, and see how it changes with the solar cycle. So that could be a project for someone to take a month's worth of data and analyze it to give us their counts for an ongoing graph and solar to show the solar radio variability. And then my last slide here is just to reiterate that Radio Jove is turned a corner in a way. We have digital systems and more advanced systems now that we can do a little bit more science with. And we're hoping to attract more people to get involved. We are currently making videos and putting materials together to help people learn. So we're calling them training modules. So for someone who's an amateur, they could run through these sort of self-paced modules to learn a little bit more about radio astronomy and some of the data that you can get with a Radio Jove type system. And so we're planning for our solar burst, solar eclipse events for later this year and then in 2024. And we're a great partnership with our Sarah groups around here, Society of Amateur Radio Astronomers. I know many of you are members there, so we have a great partnership with them, and looking forward to getting people having fun with us, right? Doing radio astronomy. I guess that's what it's all about. So I'll stop and thank you for your kind attention, and I'm happy to take questions.
Yeah, we've got some time for questions.
So I see a couple of in the chat here. Somebody asked about the recommended noise source for calibration. Yes, that is a great question. And offhand, I can't think of the source that we use, but it's essentially a broad noise source. And 100 million Kelvin in antenna temperature that you can use, and essentially you have to calibrate your calibrator, right? So whatever noise source you do use, you use a known, calibrate it with a known source, and then use a step attenuator to step through the levels, but also you can step through, different frequencies to get you the multi-step calibration. But I apologize, I can't think of the name of a particular noise chip diode that we use. Does anybody know that that's on the call here?
I just thought you might have one offhand, like a recommended one. But
I can get you that information, but no, I don't have them offhand, but I know you can find them, eBay and others places that you can get them.
well, I feel like I'm sort of trapped here at home, waiting for the pandemic to cease so I can go out and set up the giant antenna. So I'm looking for something to do while I'm waiting, since I'm not a very patient person by nature. That's all.
Well, as I said, we have plans that are for a do-it-yourself calibrator, and they're currently being beta tested. So Larry, the one in Georgia, I know is building one at the moment, and once we sort of have it vetted, we'll put that on our website, and that should have a complete parts list for you. But in the meantime, if I can find out what that is, I'll send it to Paul, and he can distribute it at a later date.
Thank
Yes,
you.
we can do that.
Next question, I guess, here from Diane about a quad helix. And so, yes, lots of different antennas will work. People have had success with like a Moxon type antenna that takes up a little bit less space too, and Yagis, crossed Yagis, they're all fine. The problem, of course, as you know, is that you've got to mount these things, and you've got to it comes with its own set of installation problems. So and expense, right? So many types of antennas. Log periodics are great antennas. Conical spiral antennas work very well. Good polarized antennas. So there are many options. If you've got the capability and the money to buy them. So certainly the quad helix works. And Rodney asked about hot Jupiters from other stars. That is a great question, and there's a group the group in the UK, the LOFAR group, low frequency group, in particular, some of the French that they're doing that. They're actually using these large arrays to search for hot Jupiter-like radio emissions from exoplanets around other stars. The idea, of course, being the Jovian emissions locally here are highly beamed, and that cone that I was the picture that I was showing you, those cones, it's a maser type mechanism, so it's amplified and coherent radio emission from the nature of the plasma in the Jovian field. So that interaction with the plasma and the magnetosphere, it can amplify the signals. And so in the directivity, just like a pulsar, gives you a very strong signal in a particular time or a particular location. So people are looking at this to see if a Jupiter-sized planet that might be closer to a star, could there be stellar magnetic, stronger stellar magnetic interaction? And in theory, the answer seems to be yes, but no one's made those observations yet. I mean, the real problem is, of course, the inverse square law, right? Those things are so distant, that the signals get so weak, and certainly with small single antenna equipment that we're talking about here, I don't think it's possible. But with professional equipment, they're doing searches right now, but to my knowledge, I don't know that they have made any positive detections yet. Ted, you've got an RSP2 receiver. Absolutely, it will work. Yes, the RSP1A and the RSP2 models of the SDR Play are the two receivers that have the right API that we can pair with our software. Otherwise, you've got to use the SDR console software for other SDRs. So the SDR Play 2 and 2 Pro are much better receivers than the 1A, for sure. I mean, they're dual channel, which is certainly very nice if you have a dual polarization antenna. But the noise figure is much better. But of course, you're paying a little more for them. But those are excellent SDRs. I don't know. Is it Sajad? Is that correct in the way I'm pronouncing it? That you're asking why Jupiter emission observed at different polarizations from northern and southern hemisphere. Yes. So the way a radio wave is emitted from moving particles, so you're getting into essentially plasma physics here. You've got a accelerated charged particle, and it's typically spiraling down field line, and the particle interact. So the electromagnetic interactions will generate electromagnetic waves, so EM waves, and there's modes. Right hand polarized mode and a left hand polarized mode of emission, and essentially due to the type, the density of the plasma and the strength of the magnetic field and a few other things I'm probably forgetting, that the right hand mode is favored. Right hand circular polarized mode is favored coming from the magnetic poles of Jupiter. In the northern hemisphere, of course, the magnetic field is pointing out, and so you get right hand circular polarization. In the south, the magnetic field is pointing inward, and so even though it's the same wave generation mode, those emissions come out as left-hand circular. I hope that makes sense. So, but you can identify that polarization is, and you do get other modes, but they're weaker. Like you can get left-hand polarized emissions from the northern hemisphere, and right-hand from the southern, but they're much weaker, and so you need essentially spacecraft, I think, to be able to observe those, or a large array. How about amateur on the lunar far side? Oh yeah, wouldn't that be the kind of a holy grail of a radio antenna, right? And gosh, I mean, I'm hearing more and more people talk about this, and you know, I think people are making plans for this kind of thing, and I don't know if that means sort of dropping antennas from an orbiting spacecraft, or they just stick into the ground and you've got a bunch of dipoles or monopoles out there. I don't know, but that would certainly be a great site to make observations from, and I'm pretty sure it's going to happen at some point. You know, once we get, I don't know, maybe more robots or more people running around on the moon up there, maybe doing something on the dark side, the far side, would be well, it would be the dark side for radio astronomy, wouldn't it? Would be definitely possible. Can I repeat the reason of the S-burst arcs we saw on the waterfall plot? So the Jupiter has two basic types of emission we call longer milliseconds, or I should say up to several seconds of bursting, called L burst or long burst, and then the S burst or the short or millisecond bursts, and those are both differ in magnitude and in intensity. In some cases, and frequency, but those two types of bursts are just different energies, different environments, and the S bursts typically come from, make sure I get this right. These are related, as far as we know, related to Io only. And so the electrical magnetic connection between Jupiter and Io creates we call a flux tube. So a plasma conduction mechanism along magnetic field lines that run through Io and Io Taurus. And so you get a little bit more energetic electrons in some cases, and so you get stronger emissions there. And so the S bursts tend to be a little bit more coherent and therefore stronger, but that coherence is very short-lived. So whatever maser, we call it the cyclotron maser instability mechanism. That's the technical term for how these radio waves are emitted at Jupiter. But think of it as groups of electrons organized in motion up and down. So there's magnetic mirroring, right? As you get closer into the pole, those electrons stop and turn around and come back. So you get enough electrons that are organized, moving coherently, and then emitting coherently. You can get really very strong bursting. And so that bursting is directly related to the emission source. And that coherence, doesn't last very long. And so there's lots of bursting and non-bursting that happens for those electrons. And we know, based on the sounds and the frequency drift, that those electrons have mirrored and then are moving back up the magnetic field line. So it's not the other way around. It's electrons are moving outward, and that causes a conical shaped emission beam, if you want to think of it that way. And then when that points towards you, Earth in this case, we pick up very strong radio signals from Jupiter. Is an SDR much better than an old analog receiver? And it is much more sensitive. That is, the answer is yes. But the old analog systems still work great. They are great. They give you better dynamic range, really. So that's the advantage of the analog system. So the SDRs tend to overload. So you do have to be careful there, but the sensitivity is much better for the SDRs. Oh, you've tried Jove 15 years ago because my antenna wasn't good enough. Yeah, as you know, it's receiver and antenna, so you've got to have a good enough in both of those categories to make your observations. But you know, part of the reason for Radio Jove is to try to guide you, give you the tools, the information, and or the hardware if you want it, to make you successful. But gosh, you know, like everything else, you know, we're all fighting interference, and that's creeping everywhere. So I used to be able to do some radio astronomy here on campus in front of my building, but no longer. I had to move out to our dairy farm, and so it's not quite as convenient as walking out the front door to get to your antenna or have your receiver in your office there. But you know, some challenges are always you're always having to overcome some challenges there. Any other questions? Did I get all of them from the chat?
Yeah, I think you've captured all the ones from the chat, Chuck.
Yeah, go ahead.
Thank you very much. Yeah, that was really interesting.
Oh, my pleasure.
Yeah, thank you for joining us and the time you put into preparing that for us. I didn't see too many volunteers for station maintenance to Andrew Thomas's question. Maybe we should continue to think about that one. Yeah, we'll see you again, Chuck. Thank you very much.
Oh, you're more than welcome. I think I'm going to hang on, and I want to hear what the students up to. Sounds interesting. Well,
yeah, we've got an early career scientist with us this evening, still in high school, and we're very pleased to give some time to Dylan, Mr. Dylan Scott. So, Dylan, our monitors are yours.
Can you do the recording, Paul?